Okay, so this is a quick hit on the inclined plane. The idea is that instead of being on flat ground, you're on some kind of weird hill and you've got some funny angle to deal with, and your job is to find the dynamics. So we'll take a look at the basics of this, and then I'll show you a real example problem at the end that might be a little more complicated than just the basics. So the first thing to do is the same thing you would do in any problem, which is look at the forces. So what are the forces? There's the weight, of course, which points straight down. The Earth doesn't care whether you're on a hill or not. It pulls you down. The thing that is a little bit different, though, is the normal force. The normal force is, of course, the force that the surface pushes on you. Now, the normal force is called normal because normal means perpendicular. And so in order to be perpendicular in this case, I have to be at that funny little angle pointing upward. So what do we do from here? Same thing we always do. Make a free body diagram, put the forces on the free body diagram. What do you do after this? Well, normally what we would do is we'd break into x and y components. And how do you do that? Well, you find the component that points along the x, you find the component that points along the y, and we could do that in this case. The only thing is we may not want to because this block is not moving in the x or y direction, is moving in both, which means you have acceleration in two directions. That's not that big a deal, but physicists are pretty lazy, and if we don't have to have two non-zero equations, we'd rather not. So is there a way where we can rig it so at least one of these is zero? Yeah. What we do is, instead of looking at the x and y directions, we put one direction parallel to the plane and the other direction perpendicular to the plane. So parallel to the plane along the direction of motion, perpendicular to the plane along the direction of motion. And so you might say, well, what do we do with that? Same thing you do otherwise. You find the component that is parallel to the plane, you find the component that is perpendicular to the plane. The good news now is that the acceleration in the parallel direction, well, that's not zero, but in the perpendicular direction, it is zero. It's zero for the same reason that when you're on the ground, the acceleration in the up-down direction is zero. You don't break through the ground, and you're not going to break through this inclined plane either. So great. Let's actually get some real work done. We'll start labeling these things. You got mg pointing down, n pointing up. If you want to find these components, you're going to need some angle. So let's pick the angle phi right there. And then in that case, we find the parallel component by cosine phi, and we find the perpendicular component by sine phi. If you're twisting your head and doing all sorts of weird things, maybe I can help you out a little bit with that. Here's this same triangle. If we rotate it, now everything's the way it would normally be, and you can see that the side that is adjacent will go like cosine phi, and the side that is perpendicular or opposite will go like sine phi. Okay, so we've got that all squared away. The only problem we still have is that what is phi? Phi isn't given in the problem. In the problem, they talk about theta. We should really put everything in terms of theta. So let's fix that. Phi is actually up there. You can see, look, if I extended this triangle, you'd end up with something that looks like this. And so actually, this is not such a big problem because theta is pi over 2 minus phi, and sine of theta equals cos phi, which means all the cosines become sines and all the sines become cosines. Boom, ready to rock. Okay, so what's the next step? Now that we have our components, we write Newton's second law in the perpendicular direction. That equals 0 because the acceleration is 0 in the perpendicular direction. We write it in the parallel direction. And this is not so interesting. What shakes out is that the normal force has to balance the component of weight that points perpendicularly. What is, I guess, interesting is that if you put something on an incline, if you want to know how fast it's going to go, right? Look at the angle you put it at. Okay, let's do a real problem now, right? Let's say instead that we've got a box, it's on an incline, and some joker is pushing straight into the incline, like trying to break it through the incline. And now we need to take that into account. And also they're telling us there's friction, so we're going to have to deal with that now as well. So how do we proceed? Same as we always do. We make a free body diagram. Let's just go through this. There's the weight. There's always weight, right? There's the normal force. We talked about that last time. The two new things in this case are, look, there's friction. Friction points along the surface and opposite the motion. This person is pushing it in this direction, so the friction points opposite that. The other thing is the force. The force is drawn on the diagram. It pushes directly in, and we just put it exactly as it is. And so now our goal is the same as it was last time. We need to break the weight into parallel and perpendicular components. So I've just put them there so that it's a little easier to work with later, but it's the same thing we did in the last case. Okay, so let's get rid of that mg. We don't need it anymore. We're not going to put it in our equations. We're going to use the components. And now we can just do the same thing for f. So how do I make the components of f? More or less like that. So I've got a parallel and a perpendicular component. Let's get rid of the resultant vector, which I'm not going to use. We only want the components. Great. Now everything is lined up. Things are either in the perpendicular or the parallel direction, and I know what to do. I write Newton's second law in the perpendicular direction. Great. I should have n. I should have n. I should have mg cos theta, and I should have f sine theta. N, mg cos theta, f sine theta, and that equals ma perpendicular, which is 0. That's why we set our axes up this way. Next, sum of the forces in the parallel direction. What does that look like? It looks like all the forces that we've listed in the parallel directions. Notice I put a plus sign in front of things that point up and a minus sign in front of things that point down the ramp. You don't have to do it that way. I just chose to do it that way because I assume the box is going to move up this way, and in that case I want to call the acceleration positive if it is, and so I label things that point that way plus, things that point the opposite get a minus sign. Remember, the only reason you have signs in physics is to say directions. Okay, all right, now it's just algebra town. Algebra, algebra, algebra. There's the normal force. We plug in from the normal force. You can plug into our equation over here. If you do that, you get a whole bunch more algebra. And then look, at the end of the day, if you take all these numbers and you plug them in, you'll get approximately that number. As an exercise, you can plug them in and see if you get the same thing. I don't really want to focus on the number because who cares about the number? I will tell you the most important part of this problem is learning how to make these free body diagrams. If you understand how to make the free body diagram, then you are going to be in good shape. The equations, you don't need to worry about. It's the free body diagram. Okay, hopefully this was more helpful than confusing.